Well, thank you, Didier, for the introduction. Thank you, Moab, Lynn, and all the staff for organizing this cool workshop. So as Didier said, I'm going to talk about a work that we started together when I was in PhD with Didier and Jean, and that we completed recently during my postdoc, and deals with a bit of name dropping around volume computation and the Lasserre hierarchy, of course. So I will follow 3 steps. First, a bit of engineering insight on the Lasserre hierarchy and its application to computing the volume of semialgebraic sets. Then I will play the doctor with the resulting Lasserre hierarchy, seeing pathologies of it, maybe cures, using geometry. And I will conclude by showing how, so I will invoke a PDE to show how these Stokes constraints improve the convergence of the Lasserre hierarchy in the case of computing the volume. So let's get into it. So it's Thursday, so there has been many talks before mine. So now you know that the Lasserre hierarchy goes far beyond only polynomial optimization. It can be applied to approach different problems. I believe tomorrow we will have also talks about PDE or control. So many areas of application. And so to sum it up very briefly, you can see this framework as a 2-step framework. First, you start with your difficult problem that can be basically anything, and you first do a lifting step, which consists of rewriting your problem in a very specific form of linear optimization problem on measures, which is called the generalized moment problem. So this is the first step, which I call a lifting. I'm not the only one. And the second step, which is the Lasserre hierarchy, properly speaking, consists of a sequence of projections of these GMP onto finite dimensional vector spaces, another form of convex problems. So a typical feature of the Lasserre hierarchy, which will be useful in this talk, is the notion of Lagrangian duality. So the cool fact is that when your cost is linear and your constraints are conic constraints, you have access to the so-called Lagrange duality, so the Lagrangian. So basically, here you rephrase your problem under the form of a problem on measures, which we call a primal problem. And the idea is just consist in corresponding a Lagrange multiplier to constraints in the primal, designing constraints in the view that whose Lagrange multiplier will be the state, the decision variable in the primal. So there is a bit of a symmetry here, and that's interesting because you have a duality between functions and measures, another form of integrating functions with respect to measures. And then, so you not only have one way of doing the Lasserre hierarchy, the moment relaxations, but also the sum of squares type limits. So that are on the function side of the hierarchy. So an example of application to this Lasserre hierarchy is the application to computing the volume of a set. So here I focus on a very specific set, which is described as the non-negativity set of a single polynomial, and I assume this set K to be smooth and compact, so that everything works fair. Everything is smooth. I can do many things. So you can think of a torus, for example. And I'm interested in computing the volume of this state, which is described as a integral indicator function with respect to the leg measure. And this is not an optimization problem, but it's a difficult problem in general. So in specific cases, you can have closed form formulae or algorithms that behave well, for example, on convex sets. But such case here doesn't have to be convex. For example, torus is not convex. But it's a difficult problem, very difficult problem. Most of the solutions are probabilistic. There exists also deterministic solutions, either numerical or exact. But it's a difficult problem. And we want to approach it using the Lasserre hierarchy. So the idea is we first want to do the lifting step. So we want to formulate it as an optimization problem. So on the right figure here, so if I consider one-dimensional set case, of course here it's trivial, but it's just for representation that I put it like this. So I would like to compute the volume of K, which is the area of the blue rectangle, but I don't have access directly to this area. I only have access to the integrals of functions. So basically the green area here. So the idea will be, okay, I just want to maximize the green area such that my green shape is inside the blue rectangle, which can be written under the form of a GMP. If you want a physics intuition, in physics, you cannot directly compute a volume. What you often do is, for example, you have a shape, you want to compute its volume, but you're not only allowed to put, for example, liquids in it and to measure the mass that you get. So the idea is to know the volume of a shape. I fill it with water and I measure the mass. Water has density 1, so the mass will exactly be the volume. If you want to formulate it under the form of an optimization problem, you just say, okay, I can take any liquid, but it should be less dense than water, and I can put any amount of this liquid into the shape. And the optimal solution will be fill the shape and take the most dense possible liquid, so water. So this has a mathematical formulation, of course, here in terms of the density of my liquid, which is rho. So this is on functions, but not the dual, it's a problem on the density, which can be rephrased like this on measures. So I want to maximize the mass I put in my shape, but I can only put mass inside the shape, not outside, and less mass than water. So I should be less dense than water. And here the obvious optimal solution is the Lebesgue measure on K, whose mass happens to be the volume. So with this first step, we switch from equation 1, which is an integration problem, onto a linear optimization problem on measures. So the GMP that I introduced before. So first step done. Some words about the duality here. So as I said, you have access to Lagrangian duality in this setting. So here I rewrote the problem on measures I just introduced. So this is the primal problem on measures. And from this problem, you can derive a dual problem on functions where function W will be the Lagrange multiplier associated with this density, saturation, constraint. And this measure mu will be the Lagrange multiplier for this constraint. So in general, when you have a duality between two problems, the supremum will be smaller than the infimum. So here, this max is smaller than the infimum. This is the weak duality property. And in this particular case, we have strong duality property, which corresponds to somehow a saddle point on a surface, for example. And here you can convince yourself that I'm minimizing the integral of W. W is asked to be bigger than 1 on K, bigger than 0 outside, so bigger than the indicator of K, if I sum it up. So I'm bigger than the indicator of K. I'm minimizing my integral, so I will approach the indicator. So my integral will approach the volume. So notice that this is an infinite. Okay. But the optimal value will again be the volume. It's quite easy to see. And the second step of the Lasserre hierarchy, if I can really sum it up very compactly, just consists in looking for minimizing sequences here under the form of polynomials W with bounded degree. And then these non-negativity constraints that are still difficult to handle with polynomials are just recast in the form of sum of squares constraints. So elements that hopefully can be tackled on a computer. And there is a nice feature about these tightenings of the dual problem or the relaxations on the primal side, which is that there is strong duality also between relaxations and tightenings at each degree of the polynomial W. And the optimal values of these projections will converge to the optimal value in infinite dimensions. So very nice properties. These relaxations are really relevant because they lead to the actual optimal value asymptotically. So this is a very nice property. Any questions so far about the introduction of Lasserre volume?
In the dual formulation, how do we think about the optimal polynomial?
So that's one of the issues that I will address later in the talk. So there is no optimal polynomial for the infinite dimensional setting here. For this problem, there is no
polynomial that almost solves it or comes close. What does it mean? What's the interpretation?
In the interpretation, you mean in terms of physics?
Or
moral interpretation. So this polynomial is very jumbled. You're pushing on the graph of your polynomial. You're pushing it, but it's somehow stuck out above the indicator.
Yeah, you have the theta function, it's continuous. You put a blanket on top of it.
Exactly. Oh yeah, there is blanket also.
So it should be as tight as possible from above.
among polynomials.
Among polynomials.
Yeah. I mean, you could choose any approximator of continuous functions. But here it's polynomials.
To approximate the indicator function
Yes.
by an element in the relative.
Yeah. Yeah, that's it. Yeah, that's exactly what I'm doing. So anything else? Okay, let's go. So it's very nice in theory, but as usual, there is a huge gap between theory and practice, especially for this specific problem of computing the volume. So here we compute the area of a double disk of radius 1/4. So the area, the true area of such disk is very easy to compute. It's pi/8. And so here I plotted the optimal value of the projections in red dots, depending on the degree I allow to my polynomial W. So going from 4 to 24. So as you can, and the black line here is the optimal value in dimensions. It's the actual area of my W. So you can see that, okay, I'm getting lower and lower, but I still have a kind of huge gap here. 100% relative error, I guess, something like that. So yeah, in practice, this is not very satisfying. I would like, if you want to be serious about volume computation, you have to do better than that. Because this is a simple example. I mean, double disk, 2-dimensional. So what's the problem here? There are several problems with this formulation, but one that is the focus of this talk is that what we discussed before. The dual is an infimum, it's not a minimum. So here I can't find any continuous doubling that would be optimal for this problem. I only have an optimal function that would be acceptable here would be the indicator of failure. It's not authorized because it's discontinuous. So I only have access to minimizing sequences that converge in L1, and convergence in L1 is not very interesting in practice here. And the even worse is that we are looking for minimizing sequence in another form of a polynomial. So polynomials are good for approximating continuous functions, but when you try to approximate discontinuous functions, something happens. That also happens when you try to approximate discontinuous functions with, for example, trigonometric polynomials in the case of Fourier analysis, which is the Gibbs phenomenon here that introduces bumps around the discontinuity of my indicator function. And of course, what I'm doing when I'm solving my projections and going higher and higher in degree is I'm approximating the area under the blue curve with the area under the red curve. So these here bumps are really bad because they are introducing an error already here. And these bumps stay here when I increase the degree, they get smaller and smaller, hopefully. In terms, at least in terms of the area, but they are still here and they introduce an error that I want to get rid of if I want to be serious about the volume computation. So how do we get rid of this pathology? What is a cure? So the intuition behind this is quite simple. So if you go back to the primal, you have a primal problem on measures, you do relaxations, and you can interpret the Gibbs phenomenon as my relaxations are somehow too relaxed, too loose. So their optimal value is too high compared to the volume. So what I would like to do is tighten a little bit those relaxations by adding constraints to them. So that was really the first idea, the inspiration behind these Stokes constraints that I'm introducing now. So we want to add constraints to the relaxations. So those constraints come from a generalization of the fundamental theorem of Tacchi, which is very classical, you all know. So the integral of the derivative is the difference between the values at the boundary of my interval here, and this has a generalization to multi-D called, so it has many names, Ostrogradski formula, Green formula. As any formula, it's also called Gauss formula, of course, and it's a generalization of the Stokes theorem. So it reads like that. You replace the derivative here with the divergence operator, and here you introduce the alpha pointing normal vector, the boundary, and the surface measure. It's also called the divergence formula. So you take, for the first idea was, okay, let's take some specific f here, specific polynomials f, such that these terms cancel, this term cancels, and just add these into the last layer, into the relaxations. I said, why not directly writing this constraint, not in terms of functions here, but in terms of the measures, so it's in a weak sense. So this can be reinterpreted under the form that the gradient of the Lebesgue measure can be equal to this measure. So it's an equality between an equation between vectors of measures. And what is interesting is vectors of not necessarily measures, because here I have gradients, so vectors of distributions. So what's interesting now here is that this is exactly the optimal solution to the volume problem, as we know. So this is the mu star I get when I'm solving the infinite dimensional problem to compute the volume, the primal. This is the primal optimal solution. So this is a constraint that I can add to the infinite dimensional problem without changing neither the optimal solution nor the optimal value. So it's kind of a mute constraint in the infinite dimensional setting, but when I'm computing the relaxations, it becomes active, and the relaxations are tighter with these constraints added than without. So let's add this equation to our primal problem. So it can be written like this. And in the case specific that I actually have proposed, where k is spread by 1 polynomial and is smooth, and in this very specific case, this vector is a vector of polynomials, which is cool when I want to apply the Lasserre. Yes, Kobe.
Do you know the circuit measure is easy to compute?
I don't care.
Okay.
So the idea is that's the spirit of it. If this is constrained, so if this measure is the Lebesgue measure here, this I can take an unknown measure. The only solution will be the surface measure because it's the divergence theorem, right? So I don't need to know it in advance. It will just pop out like automatically because here I will have this measure. Okay.
This is an additional decision variable.
Yeah, you add a variable nu here, decision variable nu, and this is the constraint you're writing. So this nu will be the surface measure normalized with the norm of the gradients of G. So any questions, any other questions so far? Before I move to the third step. Yes. So yeah, that's a good point. So I'm not really making assumptions on G. G is a polynomial. Okay. This I need because if G is not a polynomial, then this is not a polynomial. So G is a polynomial. I make no further assumptions on G, but I make hidden assumptions on G because I'm asking K to be smooth and compact. So those two assumptions have an influence on G, but it's not explicit. It's not an explicit constraint on G, but rather a constraint on K. But K is asked to be smooth and compact so that my further developments are possible. Anything else? So let's move on to the last part. So improving effectively the convergence of the hierarchy. So here I put the primal problem on measures, and I'm adding my Stokes constraint here, which, as probably noticed, requires an additional decision variable here. So of course, if I do this, I will change my dual. So the dual to this problem is not the dual to the problem without the constraints, of course. So I compute a new dual. So here I have a new constraint. So I have, it's a vector of constraints, it's several constraints. So I have several Lagrange multiplier here, additional Lagrange multiplier. I have a new decision variable, so I have a new constraint here. And this is how the new dual reads. And our claim, which was suggested by Didier, was that maybe that this time here we have a minimum and not an infinite. Maybe if I do this, I will have feasible W and F that will be optimal. So using the weak duality and even strong duality, if I only the weak duality here, if I use the weak duality, if here I get the volume of K, then I'm done. Okay, and that's what we claim and what we proved in our paper. So, as I said, when you're adding the Stokes constraints here to the primal, the infinite dimensional primal, nothing changes on the primal side, meaning that nu star will still be the optimal nu will still be the Lebesgue measure on K, and so the optimal value will still be the volume of K. You will just add an additional measure here, which is completely constrained by this equation. Because of this Stokes equation, nu star has to be this. Okay. So unique solution here. On the dual side, a necessary sufficient condition for optimality here will be that those two constraints are saturated, meaning that here this is 0 and this is 0 on K and on the boundary of K. And we will have also an additional constraint here. As we are minimizing W, W is only non-negative outside of K. The other constraints are inside of K. So if W is non-negative outside of K and minimized, then W should be 0 outside of K, right? And if I want it to be continuous, I want it to be also 0 on the boundary of K. So that's the last constraint I'm considering. So here are my nice necessary and sufficient optimality conditions in the dual side. And the last key idea is to look for F under the form of a gradient. Okay, so I'm adding a derivation here. Yes, Jean?
Maybe conclusion on the fact that now W is not supposed to be greater than 1.
Yeah. So here you can see on the right figure that was put here on purpose. So W now, W is represented in red here, and here I have the indicator. Okay, so W is not required to approximate the indicator. It's not required to be bigger than this K. Okay, than this indicator here. So we are adding, by constraining more the primal problem, we are adding some slack to the dual problem. So now W is 0 on the boundary, but then it can be lots smaller than the indicator. Okay.
But still the objective value is bigger than the volume.
Yes, by weak duality, because I have duality here. This is the volume. So by weak duality, this is bigger than the volume.
So there is compensate, it's below.
Exactly.
Way to interpret this on the right hand side.
So
Constraint.
So if you look at this formula, so this W here is represented in red, and you have saturation here of this, meaning that this is 0, and so the rest here will be this yellow curve here, and the sum. So these two curves sum to 1, but we're only considering them on K. So we are really considering the function 1 on K. So when we integrate this function, we get the volume of K. There's some kind of compensation here. We are gaining slack on W because what W cannot achieve is just provided by this divergence of it. And here you can also recall of the divergence theorem, meaning that this divergence here, when you integrate it over K, you will have simplifications that will yield exactly what you need for optimality. So, as I say, we look for f under the form of a gradient, and then what happens to our optimality condition. Of course, if we are enforcing the specific form, it's not necessary anymore, because we can have f, optimal f that is not in the form, but it's still sufficient. It's still sufficient, and so this constraint, calling this thing V, becomes a Poisson PDE. Okay. This constraint here becomes exactly a Neumann boundary condition, and I just translate the condition on W in the boundary into a condition on the source term here. So here I'm landing really on a maybe the first ever PDE one sees in a PDE class, the Poisson PDE with boundary condition. So this PDE is of course well behaved. That's the reason why it's so classical. And we know for a fact, for example, that under assumptions that have constantly been relaxed over the years, that when the source term has zero mean, which should be the case here, because W should have integral equal to the volume of K, one integral of K also. So this should have an integral equal to 0 over K. So when this holds, then this PDE has a solution U, which should be instrumental to get the F here and to get the feasible solutions. So then we just dropped a candidate for optimal W star. So we propose, for example, volume of K times something, times this. It can be written either like this or like this, it's the same. And this nice function has the property that it is continuous, because it's a nice two continuous functions. And it's integral. If you look at this way of writing it, then this fraction here, when you compute the integral, you just get 1, so that you get exactly the volume of it. So it's the most intuitive function that you can get, but it's only continuous, not even differentiable, because on the boundary you have non-differentiable terms. But we only need continuous W here. So we propose this one. We deduce V star. Of course, V star has 0 mean on K, because this on K integrated on K is volume of K, and so is this. So this cancels. So our PDE has a solution U star. Then we deduce F star equals the gradient of U, and we end up with W star and F star that are both feasible for my dual problem, and such that the integral of W star is equal exactly the volume of K. It cannot be less because of the weak duality property, so it's optimal. So here is our optimizer. So here is the proof that the dual is a mean, has a mean and not an infinite one. And this is very important because now we have access to the Stokes-Weierstrass theorem for approximating these with polynomials. So no L1 approximation anymore, but a uniform approximation using the Stokes-Weierstrass theorem. That's the qualitative reason why these Stokes constraints work in practice, as I will just show now. So back to the Gibbs phenomenon. So here I'm computing the volume of a ball in various dimensions, 1 to 10, and I represented the 2D case because it's most interesting when you represent it. So on the left side, without Stokes constraints, I get the usual Stokes phenomenon, Gibbs phenomenon, which is these waves here, these bumps that introduce errors. So especially around the boundary of my disk. And in contrast, on the right side, it's with Stokes constraints and everything is smooth. And so I observe no Gibbs phenomenon anymore because I'm not approximating an indicator anymore. So no Gibbs phenomenon because there is no discontinuous function involved. So here on the table, you can see so different values for the dimension, different values for the degree, 10 or 4, for tractability mostly. So without Stokes, in both cases, we represent the relative error that we make and the time it takes to compute the optimal value. So very bad relative errors without Stokes constraints, better relative errors with Stokes constraints. Obviously, so here in degree 4, it's not perfect, but it's still much better than without Stokes constraints. And in terms of the computational time, so it's a bit more when you are adding Stokes constraints because you have additional constraints, you have additional decision variables, so you have more computations to perform in the relaxations. But that's the price to pay. If you want more information, you have to process that information. Okay, so this is an illustration, and going back to the nice theory versus practice plot. So here it's the same plot as before, the Lasserre hierarchy without Stokes constraints for the area of my double disk. And when I'm adding Stokes constraints, I'm getting quite better results. So still not perfect, still have a small gap here, but it's, I mean, it's without comparison with respect to the first one. So this one, we are much closer to the optimal value. So this illustrates how much we improve the accuracy of our projections. Any questions before I move to the conclusion? Sorry?
In time, in computation time.
Oh, I didn't take notes about the computational time here. I mean, it's so you can guess that it will be slightly more than without the Stokes constraints, but it's still so here. I mean, I did this figure like right before sending the slides, and it took me, yeah, really no time at all. I mean, here degree 24, but in dimension 2, it's very reasonable. No, not a big deal. So to conclude, I'd say that the originality of this contribution is that we propose to add PDE constraints to the GMP to improve the convergence speed of the Lasserre hierarchy in the case of the volume problem. So this has been straightforward extended to a specific scheme for volume computation that takes into account sparsity when you want to scale to higher dimensional sets. So basically the Lasserre hierarchy, as you may know, doesn't scale well. So if you want to go, for example, if you want to compute the volume of a set of in the dimension 100, for example, you cannot do it with the standard Lasserre hierarchy. So you need to exploit structures. So if you're lucky and you have structures, for example, sparsity, then you can go for dimension 100. We did it. But for the volume problem, if you don't have anything to improve the convergence of your scheme, it's quite useless to go high in the dimension because anyway, your approximations will be loose. So not very interesting, but these Stokes constraints are compatible with the sparse scheme that we devised. So we were able to combine them and to design sparse Stokes constraints to compute volumes in high dimension. But there still remains many open questions, even on this specific problem on Stokes constraints for the Lasserre hierarchy in volume computation. First and foremost, the most natural question. So I showed how the Stokes constraints improve the convergence, but I didn't say anything on how much they improve the convergence. So the first question we have to answer is the comparison between the convergence rates of the Lasserre hierarchy with and without Stokes constraints. So this boils down, and it boils down to a comparison between CK approximation and L1 approximation, and using the recent results of Lorenzo and Bernard on degree bounds on some of square representations of polynomials. Another interesting thing is to refine regularity conditions, because I exhibited one possible optimal solution, which is really minimal, meaning that W is only continuous, and then F is only C1, and that's all. But what I didn't say is that actually, if you don't want an explicit formula for W, you can go for a smooth W in the case where K is smooth. So if W is smooth, then F will also be smooth, and then it will be easier to approximate them as polynomials. So here, refinements can be done here and plug into this quantitative analysis. And of course, here I talk only about one polynomial inequality and smooth K. So we would like to go to generic basic semialgebraic sets, not required to be smooth anymore, and not required to be destroyed by only one polynomial inequality. So having several polynomial inequalities is not really a challenge. It's just more bothersome to write, but it's okay. The problem will be if K is not smooth anymore, because most PDE results on existence in solutions of in uniqueness of solutions to PDEs really use the fact that the domain on which you design your PDE is regular. So if you have non-regularities on the boundary of your domain, then it's another story. So that's the challenge here that we have to face. So as a follow-up for future work, so the first thing would be to address those open questions on the specific problem of volume, which is currently ongoing with Lorenzo and Corbinian. We are working together to get answers to these three questions. Hopefully it will be, we will get some results soon. The next step will be to export these Stokes constraints to other applications of the Lasserre hierarchy. So this idea of adding constraints to the primal problem seems quite powerful. So we would like to try it on other applications of the hierarchy. Of course, it will not be Stokes constraints anymore, because these constraints are very specific to the volume, but maybe other constraints that we could look for and find to improve the convergence of the Lasserre hierarchy in general, so specific to the application. Also, a more theoretical question would be, okay, so these Stokes constraints can be interpreted as regularization. So I think there is a link between those Stokes constraints and, for example, what Francis presented this morning on minimizing the entropy, or adding other regularizers, be it Tikhonov regularizer, for example, getting representative theorems for regularized optimization problems. So it's kind of a different community, I'd say, but it would be interesting to see the link between the two, and I'm sure Stokes constraints would fit very well in this framework. And last idea, but not least, which was suggested by Francis when we discussed this whole work together at some point this year, was, okay, this is cool for Lasserre hierarchy, but Gibbs phenomenon appears in other applications. So for analysis, for example, but also learning with reproducing kernel Hilbert spaces. Sometimes the Gibbs phenomenon shows up in this setting also. So it would be interesting to see if these Stokes constraints can be also used in this case to get rid of the Gibbs phenomenon in general. Another open question that I'd like to tackle. And so this concludes my talk. I'd like to thank you for your attention. And
many thanks, Matteo. Further questions? Yes.
On slide 8, when you compare your error.
So this one.
Yeah, this one. Can you tell us what happened in for the case n equals 6 and more, that will explain why even with those we still have a lot of corrective error compared to the degree 10 case
So, yeah.
number of variables.
First explanation is here I'm degree 4, which is really, I mean, I think it's the first degree of the hierarchy that makes sense and that takes into account the Stokes constraints.
Okay.
In degree smaller, the Stokes constraints are just ignored. So it's the first degree that you can take. So really, when it's the more problems, so you're not at the same level of accuracy here, of course.
Okay.
So
for
that's a
example,
first explanation.
If I were to go to D equals 6 or 8 with N equals 6.
Yeah, it would be better.
Yes, okay.
And then even with this, so this would improve, of course, I mean, it's the usual way of doing the Lasserre hierarchy, you just go higher in the degree to improve the accuracy. But you would, of course, first face size issues if N is too big. And second, if the degree, I mean, above degree 20 makes not much sense to increase the degree in this specific setting. So there is another, so here, so yeah, I mean, I'm starting to getting more visible again, and I still have a small gap here. And this is more linked for, we believe that it's more linked to the choice of the basis you use for the the vector space of polynomials. And the monomial basis is not the best one because your monomials, when you go to high degree, just become the convex indicator of -1.
Chebyshev polynomial, you can decrease further.
Yeah, they did it with Chebyshev, so in the first
The
volume.
original volume,
Yes.
with Chebyshev.
13 years ago.
Improvement, but for degrees bigger than 20.
Yeah, you can go higher into degrees, so, and it makes sense to do so with the Chebyshev basis.
Yes, I comment on the Stokes constant. I would see that more what we could call physics-informed optimization.
Exactly, yeah.
Like they do in
That's basically physics
the
informed.
problem where you know the advanced solution, the indicator of the okay, and any information that you have from this solution, and Stokes constraints are one particular information, and which is linear at the moment. So if you add this information, you don't change the optimization problem, but the relaxation becomes much more.
Yeah.
So it's very well known in combinatorial optimization. So adding constraints in the problem doesn't change the problem, and in the relaxation, yes.
Yes.
It's exactly this phenomenon.
Yeah. So you can look for in general, if you know in advance the optimal measure, you can look for, but it's abstract for the kind of orthogonal to this optimal measure. So the set of functions that have zero integral against this measure, and just add these constraint that the integral of these functions with respect to this measure is always 0. For example, that's an idea. There are several ideas, but you need to identify those specific type of functions. Yes.
In the previous slide again, you said that without the constraints, it's a bit faster, while it's up to 50 times faster there, as far as I can see. Where is the time spent? Is it due to the additional variables in the tool of the SDP solver?
So there's, I'd say, the most significant increase in time should be in the solution of the SDP, because you're adding values and constraints that. So you're not. The biggest matrix you're dealing with is the same size as before, but you have more matrices to deal with. So that's the reason why but as it doesn't change the size of the biggest matrix, you can hope that the computational time won't grow too quickly with respect to this, but it still grows a bit. Yeah, maybe linearly, but not more.
Maybe we can take last one. Bernard was raising his hand, so and then welcome you to discuss about the coffee break. So Bernard, the last one.
So it's a naive and maybe provocative question. So you can also approximate the indicator function by piecewise linear function on the mesh, and then compute the volume in this way. So how is there a comparison of this, say, basic or pragmatic approach with this?
So you would need piecewise. So you propose piecewise affine functions.
For example, for your equation G, you can approximate the graph.
Mhm.
G equals 0 by some sequence,
Yes,
and then compute,
then compute the volume of the polytope that you get. Yeah, you could do that. You could do that.
did you compare? Or is there-
No, we didn't compare, and honestly have no idea how we could compare.
The only other techniques we know of are either rather old, and they are mostly probabilistic. They are sample, based on sampling, and there is much more recent work of people in the room, Pierre Lérel, Mohamed Safed, and Marc Mézarova, yeah, which is a blend of symbolic numerical techniques and which is aimed at getting very, very accurate approximations. But for what you suggest, Bernard, I don't believe you said that ever attempted or studied.
No, that's a,
Maybe it will be
that's a blind
basic
spot.
signals.
Of this,
But we surveyed the
yeah, we
this-
haven't seen it, and we didn't
haven't
think
seen
about it.
Doesn't mean that it doesn't work. But
Yeah,
maybe people tried, it failed, maybe not.
I get the bottleneck of kind of Nielsen with the dimension.
Yeah, but the dimension, the meshing in high dimension would be very expensive, but you know, we don't go that far without exploiting the processes. We do not say we can solve problems of very high dimension without sparse.
no, we can't.
And I don't know for symbolic techniques, how far you can go in terms of number of variables. Yeah.
For spheres, the high,
Yeah.
compared to before.
Okay, so this concludes this talk. Many thanks, Matteo, again.
Thank you.